the safest place in the universe might be the one no one knows exists. Earth is not that place. Not anymore. For over a century, every radio broadcast, every television signal, every radar pulse from every airport and military base on the planet has been leaking off the surface and traveling outward at the speed of light. This was never a decision anyone made. There was no vote, no treaty, no moment where humanity chose to announce itself to the cosmos. It simply happened, a side effect of learning how to talk to each other across distances. And now there is a sphere of human noise roughly 200 light-years in diameter, expanding in every direction, washing over star system after star system. Anything within that sphere with the right kind of receiver already knows a something lives here. Depending on what they can decode, they may know far more than that. Most people have never given this a second thought. The assumption, if it comes up at all, is that the universe is either empty or welcoming. That if something intelligent were out there, contact would be a moment of wonder, the greatest discovery in human history. But there is another possibility, one that a growing number of physicists, mathematicians, and game theorists have taken very seriously. And it begins, not with hope, but with a question that has gone unanswered for over 70 years. The observable universe contains roughly 2 trillion galaxies. Each one holds, on average, around 100 billion stars. A significant fraction of those stars have planets, and current estimates suggest the number of potentially habitable worlds in the observable universe exceeds the number of grains of sand on every beach on Earth. That is not poetic exaggeration. That is the actual ratio the math produces. The number of places where life could arise is so vast that no human mind can hold it as a single thought. Now add time. The universe is 13.8 billion years old. Our sun and its planets formed roughly 4.6 billion years ago, but there are star systems out there that are 10 billion years old. If a civilization arose around one of those older stars, even a billion years before us, the head start would be almost incomprehensible. A billion years ago, the most advanced life on Earth was a single-celled organism drifting through a warm ocean. That is the distance between us and a species that may have been building things before our planet even had multicellular life. A civilization with that kind of time could have explored, settled, or signaled across the entire Milky Way many times over. The galaxy is 100,000 light-years across. Even at a fraction of the speed of light, even with long pauses between expansions, a billion years is more than enough to leave a mark everywhere. So here is the problem. We should see evidence. Megastructures blocking starlight, probes passing through our solar system, patterns in the electromagnetic spectrum that nature alone could not produce. Something, anything. The universe should be visibly, obviously full of activity, and it is not. Everywhere we point our instruments, we find only natural phenomena following natural laws. Hydrogen clouds collapsing into stars. Galaxies drifting along gravitational currents. Chemistry and physics doing exactly what chemistry and physics do, with no apparent fingerprints of engineering anywhere. It is as if, across 13.8 billion years and 2 trillion galaxies, no one has ever built anything. That gap between what the numbers predict and what we actually observe is called the Fermi paradox. It was first articulated in 1950 when the physicist Enrico Fermi sat down at lunch with colleagues at Los Alamos National Laboratory and posed a question so simple it has haunted science ever since. Where is everybody? In the decades since, dozens of explanations have been proposed. Maybe life is far rarer than our models suggest. Maybe intelligent civilizations destroy themselves through war, environmental collapse, runaway technology, before they ever develop the ability to cross interstellar distances. Maybe the distances themselves are the answer, and the galaxy is simply too large for anyone to reach anyone else in a meaningful time frame. Maybe they exist, but are so fundamentally alien that we would not recognize their signals, even if those signals were passing through us right now. Each of these explanations carries a certain comfort. They describe a universe that is indifferent, or difficult, or just too big for neighbors to meet. They are answers you can live with. But there is one explanation that offers no comfort at all. What if the universe is full of life, and the silence is not an accident? What if every civilization that has survived long enough has arrived at the same conclusion, that revealing yourself is the single most dangerous act an intelligent species can commit? What if the reason the cosmos is quiet is that every surviving intelligence out there has learned, either through logic or through loss, to stay absolutely still? Imagine a vast forest in total darkness. You cannot see the trees. You cannot see the sky. You know you are not alone. You have heard the faintest sounds of movement somewhere in the distance, but you cannot tell how far away, how many, or what they want. And you know one thing with certainty. Whoever makes the first sound becomes the easiest target. No one calls out. No one lights a fire. No one moves unless they have to. Because in this forest, silence is not emptiness. Silence is strategy. Silence is how you stay alive. That is the dark forest hypothesis, and it does not describe a universe with no one in it. It describes a universe where everyone is in it, watching, calculating, staying hidden, because the cost of being found could be absolute. Now consider Earth again, a planet that has been radiating electromagnetic signals in every direction for 100 years. A planet whose inhabitants have, on multiple occasions, deliberately aimed powerful transmissions at other star systems. A planet that has launched physical objects beyond its own solar system, carrying golden records engraved with diagrams showing exactly where it is. If the dark forest is right, we have not been doing something bold. We have been doing something catastrophically reckless. We have been lighting fires and shouting into the darkness in a forest. We do not understand, surrounded by hunters we cannot see. This is not a story about whether aliens exist. This is a story about a piece of logic, cold, clean, and very difficult to dismiss, that takes a handful of reasonable assumptions about the universe and follows them to a conclusion most people are not prepared for. It is a story about what silence means when the stakes are survival. And it starts with the simplest, most dangerous question a scientist has ever asked over lunch. Where is everybody? And what if the answer is everywhere and watching? The summer of 1950 was a strange time to be a physicist. The atomic bomb had been detonated 5 years earlier, and the men who had built it were still working together at Los Alamos, now turning their attention to hydrogen bombs, missile trajectories, and the mathematics of thermonuclear war. These were people who had already changed the world in ways they could not fully control, and they knew it. One afternoon, a group of them walked to lunch together. Among them was Enrico Fermi, Nobel laureate, architect of the first nuclear reactor, and one of the most intuitive physicists of the 20th century. Fermi had a gift for what his colleagues called back-of-the-envelope calculations. The ability to take a complicated problem, strip it down to its essentials, and arrive at a surprisingly accurate answer with almost no data. He once estimated the yield of the Trinity nuclear test by dropping scraps of paper into the blast wave and measuring how far they moved. He was off by less than a factor of 2. That afternoon, the conversation at lunch had turned to a recent wave of UFO sightings making headlines across the country. Flying saucers, unexplained lights, the usual mix of hysteria and speculation. The physicists were joking about it. debating whether some of the reports might be secret military aircraft, when Fermi suddenly went quiet. Then, in the middle of an unrelated conversation, he looked up and said, "Where is everybody?" The table went silent. Everyone understood instantly what he meant. He was not asking about UFOs. He was asking about the math. Fermi had run the numbers in his head, roughly, rapidly, the way he always did. The galaxy is old. It is large, contains hundreds of billions of stars, many of them far older than our sun. Even under conservative assumptions about how often life arises, how often it becomes intelligent, and how often it develops technology, the expected number of detectable civilizations in the Milky Way alone should be significant. Some of them should have had millions or even billions of years to expand. The galaxy should be colonized, or at least noticeably altered by now. The evidence should be everywhere. And there was nothing. Fermi did not publish a paper about this. He did not present it at a conference. It was a lunchtime remark, almost a throwaway. But the question burrowed into the minds of everyone at that table, and eventually into the foundations of an entire field of scientific inquiry, because the more carefully anyone examined it, the worse the problem became. 11 years later, a young astronomer named Frank Drake tried to do what Fermi had done in his head, but on paper and with more structure. Drake was preparing the first systematic search for extraterrestrial radio signals, a project called OSMA, run from a radio telescope in Green Bank, West Virginia. Before the search began, he wanted a framework for estimating how many civilizations might be out there transmitting signals right now. The result was the Drake equation. It is not really an equation in the mathematical sense. It is a chain of probabilities, a way of organizing our ignorance. It starts with the rate of star formation in the galaxy, multiplies by the fraction of stars that have planets, then by the fraction of those planets that could support life, then by the fraction where life actually arises, then by the fraction where life becomes intelligent, then by the fraction that develops technology capable of sending detectable signals, and finally by the average length of time such a civilization remains detectable. Multiply all of those terms together and you get N, the number of communicating civilizations in the Milky Way at any given moment. The beauty of the Drake equation is that it gives you a structure to work with. The problem is that, in 1961, almost every term in it was a guess. Drake and his colleagues sat in a room and assigned rough values. They estimated that roughly 1 new star forms per year in our galaxy. That much was known. They guessed that perhaps 1/5 of stars had planets. 1/5 of those had conditions suitable for life, and life arose on all of them where it could. Intelligence and technology, they assumed, were rarer. Maybe 1 in 10 civilizations that developed life also developed intelligence, and 1 in 10 of those built something we could detect. For the final term, the average lifetime of a communicating civilization, they threw out a number. 10,000 years. The answer they got was 10. 10 civilizations right now in the Milky Way, sending signals. That number has been debated, adjusted, and argued over for more than 60 years. Depending on which values you plug in, N ranges from 0 to millions. Optimists, and there have been many, point to the recent explosion of exoplanet discoveries. We now know that almost every star in the sky has at least 1 planet. Rocky worlds in habitable zones are not rare, they are common. The fraction of stars with suitable planets is not a guess anymore. It is a measurement, and the measurement is far more generous than Drake's original estimate. Pessimists focus on the terms we still cannot measure. How often does chemistry become biology? How often does biology produce a brain capable of abstract thought? How often does abstract thought lead to radio telescopes? We have exactly one example: ourselves. and a sample size of 1 tells you almost nothing about probability. For all we know, the emergence of intelligent life on Earth required a sequence of events so unlikely that it has happened only once in the entire observable universe. We might be a statistical freak, the one lottery ticket that hit out of trillions that did not. This tension between cosmic abundance and observed absence is what gives the Fermi paradox its enduring power. The optimistic reading of the Drake equation says the galaxy should be full of voices. The sky says otherwise. Something is off, and over the decades, a long list of proposed solutions has accumulated. One of the earliest and most intuitive proposals is that intelligent life is simply far rarer than we imagine. This is sometimes called the rare Earth hypothesis. The argument is that while simple microbial life may be common, chemistry turning into biology under the right conditions, the leap to complex, multicellular organisms requires an extraordinary chain of circumstances. Earth had plate tectonics to recycle its atmosphere. It had a magnetic field to shield it from solar radiation. It had a large moon to stabilize its axial tilt, keeping seasonal variations moderate over billions of years. It had Jupiter acting as a gravitational shield, sweeping up many of the asteroids and comets that might have otherwise sterilized the surface repeatedly. Remove any one of these factors, and the story might have ended with bacteria. Intelligent life, in this view, is not just uncommon. It is a miracle that required a planet with an almost absurdly specific resume. Another class of solutions focuses not on how life begins, but on how it ends. The concept is called the Great Filter, a term coined by the economist Robin Hanson in 1996. The idea is simple but disturbing. Somewhere between dead chemistry and a galaxy-spanning civilization, there is a step that is almost impossibly hard to pass. A bottleneck so severe that virtually no lineage makes it through. The question is where that filter sits. If the filter is behind us, if the hard part was the origin of life itself, or the jump from single cells to complex organisms, or the evolution of intelligence, then we have already passed it. We are the rare survivors, and the universe ahead of us is open. That is the comforting version. If the filter is ahead of us, if the hard part is something that happens after a civilization becomes technological, then we have not yet faced the thing that kills everyone else. That is considerably less comforting. And when you look at human history, it is not hard to imagine what that filter might be. Nuclear weapons, climate collapse, engineered pandemics, artificial intelligence that escapes its constraints, technologies that give a civilization the power to destroy itself faster than it develops the wisdom to avoid doing so. A third category of explanations avoids the question of survival entirely and focuses on detection. Maybe civilizations are out there, thriving, but we simply cannot see them. This could happen for several reasons. Our search has been going on for only a few decades, covering a tiny fraction of the sky at a limited range of frequencies. We have been looking for radio signals because that is what we know how to build. But an advanced civilization might communicate using methods we have not yet discovered. Gravitational waves, neutrino beams, quantum entanglement, or something entirely outside our current physics. Searching for alien radio signals might be like standing on a beach with a pair of binoculars and concluding the ocean is empty because you cannot see any fish. There is also the zoo hypothesis, the idea that advanced civilizations are aware of us, but have deliberately chosen not to make contact. Perhaps we are being observed the way a researcher observes an uncontacted tribe, with interest but without interference. Perhaps there is a kind of cosmic etiquette, a consensus among older civilizations that younger ones should be left alone until they reach a certain threshold of maturity. This is an elegant idea, but it requires a level of coordination across thousands or millions of independent civilizations that is difficult to justify. And then there are the more exotic possibilities. Perhaps we live inside a simulation, and the emptiness is a feature of the program. Perhaps the universe is teeming with intelligence, but in forms so different from our own. Distributed consciousness, embedded in stellar magnetic fields, or slow-thinking organisms the size of gas giants. That the concept of communication, as we understand it, simply does not apply. Each of these solutions has attracted serious thinkers. Each of them resolves the paradox in a way that is internally consistent, but none of them has gained anything close to consensus. Because none of them can be tested with the tools we currently have, we cannot yet measure how often life arises on other worlds. We cannot survey the galaxy for megastructures with any completeness. We do not know enough about the long-term trajectory of civilizations to say whether self-destruction is the norm. What we are left with is a menu of possibilities and no way to choose between them. The paradox remains open, a wound in our understanding of the cosmos that refuses to close. But in the early 2000s, something changed. A new answer emerged, not from a physicist's blackboard or an astronomer's dataset, but from a novel. And unlike most proposed solutions, this one did not try to explain the silence by pointing to a single missing variable. Instead, it took the silence itself and turned it into the central feature of how the universe works. It argued that the cosmos is not empty, it is not indifferent, it is not too vast for contact. The cosmos is a system, one governed by a logic so stark, so fundamentally tied to the mathematics of survival, that any civilizations advanced enough to understand it would reach the same conclusion independently. Stay hidden. Stay quiet, and if you ever detect someone else, act before they do. The answer did not make the silence less strange. It made the silence make sense. And that, for many who encountered it, was far more frightening than any of the alternatives. The idea did not appear out of nowhere. It grew slowly, across decades, in different minds working on different continents, each one circling the same uncomfortable thought from a slightly different angle. In 1983, the American astrophysicist David Brin published a paper called The Great Silence. It was an ambitious attempt to catalogue every proposed explanation for the Fermi paradox in a single, systematic framework. Brin sorted the solutions into categories, weighed them against each other, and in the process flagged something that most discussions had been politely avoiding. Among the possible explanations was one that did not require exotic physics or rare biology. It simply required fear. Brin raised the possibility that advanced civilizations might deliberately avoid detection, not because they lacked the ability to communicate, but because they had concluded that communication was dangerous. He did not develop the idea much further. He noted it as one option among many and moved on. But the seed was there. Around the same time, science fiction author Greg Bear was exploring a closely related idea in fiction. His 1987 novel, The Forge of God, told the story of Earth's destruction by self-replicating alien machines. Weapons launched by a civilization that systematically annihilated emerging worlds before they could grow into competitors. Bear's premise was blunt. The universe was not empty and it was not kind. It was a place where power projected at interstellar scales had only one practical application, and that application was elimination. The novel was disturbing precisely because it offered no villains in the traditional sense. The civilization doing the destroying was never fully revealed. It did not explain itself. It did not negotiate. It simply acted the way an immune system acts against an unfamiliar cell. Automatically, without malice, because the logic of self-preservation demanded it. These were fragments. pieces of a picture that had not yet been fully assembled. The thinker who brought them together into a single, rigorous, deeply unsettling framework was a Chinese engineer and novelist named Liu Cixin. Liu grew up in a coal mining region of China's Shanxi province during the Cultural Revolution, a period of ideological upheaval, political purges, and institutional collapse. He trained as an engineer and spent years working at a power plant before turning to science fiction. When he began writing, he carried with him a sensibility shaped not by the optimistic, space-age narratives of Western science fiction, but by a first-hand understanding of how quickly civilizations can turn on themselves, how fragile institutions are, and how the logic of survival can override every other value when the pressure becomes great enough. His trilogy, Remembrance of Earth's Past, was published in China between 2006 and 2010, and later translated into English, where it became an international phenomenon. The first novel, The Three-Body Problem, dealt with first contact and its consequences, but it was the second novel, published in 2008, that introduced the idea that would come to define the series and reshape how millions of people think about the cosmos. The book was called The Dark Forest. Liu's argument is built on two axioms. He presents them not as opinions or assumptions, but as foundational truths. Starting points that any civilization, anywhere in the universe, would eventually recognize. The first axiom is that survival is the primary need of every civilization. This sounds obvious, almost trivially true, but Liu frames it in a very specific way. He is not saying that civilizations value survival above all else as a conscious moral choice. He is saying that the universe has already selected for this trait. Over billions of years, any civilization that did not prioritize its own continuation, that was reckless with its safety, that exposed itself to unnecessary risk, that trusted strangers without verification, is no longer around. What we observe in the universe today, if anything is out there, is the residue of what survived. And what survived, by definition, is what treated survival as non-negotiable. This is not a philosophical claim, it is a filtering mechanism. The universe does not need to enforce the rule. Time enforces it automatically. The second axiom is that the total matter and energy in the universe is finite. Again, this seems straightforward. Stars have lifespans. Planets have resource limits. Even in a cosmos of staggering scale, there is a ceiling on what is available within any reachable volume. And as civilizations grow, as they expand, develop new technologies, increase their populations and their energy consumption, their demand for resources grows with them. Two civilizations in the same region of space are, in the long run, drawing from the same pool. They may not be competing today, but the trajectory of growth ensures that eventually they will be. These two axioms alone do not produce the dark forest. What produces it is a third element, something Liu calls the chain of suspicion. Imagine that civilization A detects civilization B-A, does not know B's intentions. B might be peaceful, B might be aggressive, B might be indifferent. A has no way to determine which, because the only way to learn about B is through communication. And communication across interstellar distances takes years, decades, or centuries. A message sent to a star 50 light-years away will not receive a reply for at least 100 years. But the problem goes deeper than delay. Even if B responds and says, "We are peaceful," A has no mechanism to verify that claim. B might be lying. B might be sincere now, but might change its mind in 1,000 years. B might be governed by a faction that wants peace, but another faction within B might seize power tomorrow and decide otherwise. A cannot monitor B's internal politics across light years. A cannot inspect B's weapons. A cannot build the kind of trust that, on Earth, requires physical proximity, shared institutions, repeated interactions, and enforceable agreements. None of those things exist between stars, so A is left guessing, and A knows that B is also guessing about A, and A knows that B knows that A is guessing. This recursion, I think that you think that I think, has no end point. There is no level at which either side can reach certainty about the other's intentions. The chain of suspicion is infinite. On Earth, we have mechanisms to break chains of suspicion. Treaties, trade, diplomacy, shared membership in international organizations, physical inspections, mutual economic dependence. These tools work, imperfectly, but they work. Because Earth is small, because communication is fast, and because there are institutions with the authority to mediate and, if necessary, punish violations. Between stars, none of these tools exist. The distances are too great. The communication lag is too long. There is no interstellar court, no shared economy, no mutual dependency that makes betrayal costly. And then there is the final element that closes the trap. Liu calls it technological explosion. Humans went from the first powered flight to a nuclear weapon in 42 years. From the invention of the transistor to a global computer network in about 50. From the discovery of DNA's structure to the ability to edit genes in roughly 60. Technological progress is not linear, it accelerates. And the rate of acceleration is itself unpredictable. Now, apply this to the interstellar scenario. Civilization A detects Civilization B and determines that B is currently primitive, perhaps at a level equivalent to Earth's Bronze Age. A concludes that B is harmless. B has no space travel, no advanced weapons, no ability to threaten anyone. Why worry? The answer is time. What looks like a Bronze Age civilization today could undergo its own technological explosion and become a spacefaring power in what amounts to a blink of an eye on cosmic timescales. A few thousand years, trivial against the backdrop of galactic history, could transform B from a harmless curiosity into an existential rival. And once that transformation happens, it may be too late for A to respond. The window in which A could have acted safely has closed. This is what makes the dark forest logic so difficult to escape. It is not about what another civilization is. It is about what it could become. And because technological explosion is rapid and unpredictable, the only safe assessment of any other civilization's threat level is, eventually, potentially lethal. Commode all three elements: the drive to survive, the chain of suspicion, and the threat of technological explosion. And the logic arrives at a conclusion that feels monstrous, but follows with almost mechanical inevitability. When Civilization A discovers Civilization B, A has two options. The first is to attempt communication. But communication takes decades or centuries, cannot produce verifiable trust, and gives B time to grow. The second is to eliminate B while the cost is still manageable. Elimination is not motivated by hatred or ideology. It is motivated by the recognition that the chain of suspicion cannot be broken, that B's future capabilities cannot be predicted, and that waiting carries a risk that only increases with time. In game theory, this is a variation of the prisoner's dilemma, but played under conditions that strip away every factor that normally promotes cooperation. There is no repeated interaction because the first interaction may be the last. There is no enforcement mechanism because no third party exists to punish defection. There is no communication channel reliable enough to build trust, and the payoff matrix is asymmetric in a terrifying way. If you cooperate and the other side defects, you do not lose a few years in prison. You lose your entire civilization. Under these conditions, the dominant strategy, the one that rational actors converge on, regardless of their preferences, is to strike first. Not because it is right, not because it is desired, because every other option carries a probability of extinction that a survival-oriented civilization cannot accept. And the logic does not stop there. It applies to every civilization simultaneously. Every intelligent species in the universe, if it is rational, and if it has survived long enough to understand these dynamics, faces the same dilemma and arrives at the same conclusion. The universe becomes a system in which every participant is both a potential hunter and a potential target, and the only defense is to remain undetected. Liu's metaphor captures this with devastating clarity. A dark forest, full of armed hunters, each one moving silently through the trees, each one straining to hear the others while making no sound of their own. The forest is not empty, it is crowded. But it is silent because silence is the price of survival. In this framework, the Fermi paradox is not a paradox at all. The absence of signals, the absence of megastructures, the absence of any visible evidence of intelligence, all of it is exactly what you would expect. A civilization that builds a Dyson sphere around its star is painting a target on itself. A civilization that broadcasts radio signals is giving away its coordinates. A civilization that sends probes to other star systems is leaving a trail that can be traced back to its origin. Every act of expansion, every act of communication, every act of visible engineering is a risk. And the civilizations that took those risks are no longer around to take them again. What remains is what learned the lesson. What remains is what went quiet. There is an additional layer that makes this even more disturbing. In the dark forest, you do not need to be certain that another civilization is a threat. You do not even need to believe it is likely. You simply need to acknowledge that it is possible. Because the cost of being wrong, the complete destruction of your world, is so catastrophic that even a small probability of danger justifies preemptive action. This is not a mindset unique to alien civilizations. It is a principle that appears in nuclear deterrence theory, in cybersecurity, in insurance mathematics. When the downside of a wrong decision is total and irreversible, rational actors do not wait for proof. They act on probability. They act on worst-case scenarios. They act early. Applied to the cosmos, this means that the dark forest does not require evil. It does not require aggression. It does not even require hostility. It only requires rational actors operating under uncertainty with existential stakes. The math does the rest. Liu Cixin did not invent every piece of this framework. Brin identified the silence as strategy idea. Bear explored the logic of preemptive destruction. Game theorists had already mapped the dynamics of the prisoner's dilemma under conditions of no trust and no enforcement. What Liu did was combine all of these threads into a single, coherent narrative structure and demonstrate, with the patience and precision of an engineer, that the conclusion follows from the premises with very little room for escape. The result is an idea that has migrated well beyond science fiction. Astrophysicists reference it in papers about SETI strategy. Policy experts cite it in discussions about whether humanity should be actively transmitting messages into space. Philosophers use it to explore the limits of cooperation under radical uncertainty. The dark forest hypothesis has become one of the most discussed ideas in modern cosmology, not because it is proven, but because it is very hard to refute without challenging at least one of its seemingly reasonable starting assumptions. And that is where the real discomfort lies. The axioms are simple. Survival matters. Resources are limited. The logic that follows from them is clean and internally consistent. If you accept the premises, the conclusion is almost impossible to avoid. The only question is whether the premises are actually true, or whether, somewhere in the chain, there is a flaw that breaks the argument open. Because if there is, it changes everything. And if there is not, then The silence of the cosmos is not a mystery. It is a warning. The dark forest hypothesis has a seductive quality. Its axioms feel intuitive. Its logic is clean. The conclusion follows from the premises with an almost mathematical precision. And yet, the moment you begin pressing on those premises, testing them against physics, game theory, biology, and the actual mechanics of what interstellar conflict would require, cracks begin to appear, not small ones. Deep, structural fractures that suggest the argument may be far less airtight than it first appears. This does not mean the hypothesis is wrong. It means it depends on assumptions that are themselves unproven. And, in a question, this large unproven assumptions deserve to be examined with the same rigor that produced them. The first and perhaps most fundamental objection concerns the second axiom, that resources in the universe are finite, and that this finitude drives civilizations into competition. In absolute terms, the axiom is true. The universe contains a fixed amount of matter and energy. Stars burn out. Planets can be stripped bare. Entropy is real. But the question is not whether resources are finite in some ultimate thermodynamic sense. The question is whether they are scarce at the scale relevant to interstellar civilizations. Consider what a civilization capable of reaching other star systems would actually look like. To cross interstellar distances in any reasonable timeframe, a species would need to command energy on a scale that dwarfs anything in human experience. The physicist Nikolai Kardashev proposed a classification system in 1964 that remains useful. A Type I civilization harnesses all the energy available on its home planet, roughly 10 to the power of 16 watts. A Type II civilization harnesses the full output of its home star, roughly 10 to the power of 26 watts. A Type III civilization harnesses the energy output of its entire galaxy. Humanity is currently somewhere around 0.7 on this scale. We are not yet a planetary civilization in energy terms, but a civilization that has reached even Type II, the level necessary for serious interstellar activity. Would be operating with energy resources so vast that fighting over a rocky planet would be roughly equivalent to two modern nations going to war over a single grain of rice. The raw materials of the universe are not concentrated on planets. They are spread across asteroid belts, cometary clouds, gas giants, and the interstellar medium itself. A Type II civilization could disassemble asteroids for metals, harvest hydrogen from gas giants for fusion fuel, and collect energy directly from stellar radiation. The entire resource base of a habitable planet. The thing the dark forest assumes civilizations would kill for represents a vanishingly small fraction of what is available in any given star system. This does not eliminate competition entirely. There may be resources that are genuinely rare, specific isotopes, strategic locations, unique astronomical phenomena, but it undermines the core argument that scarcity inevitably drives civilizations into existential conflict. At the energy scales required for interstellar travel, the economics of conquest look absurd. It costs less to mine an uninhabited asteroid belt than to wage war across light years against a civilization that may itself be capable of retaliating. The second major objection attacks the game theory at the heart of the hypothesis. The dark forest models every encounter between civilizations as a one-shot prisoner's dilemma, a single interaction between strangers who will never meet again, with no enforcement mechanism and no ability to communicate reliably. Under those conditions, defection, betrayal, preemptive attack is indeed the dominant strategy. This is well-established mathematics, but the one-shot framing is itself an assumption, and it may not reflect the actual dynamics of a populated galaxy. Game theory distinguishes sharply between one-shot games and iterated games. repeated interactions between the same players over time. The results are dramatically different. In one-shot games, rational players defect. In iterated games, cooperative strategies consistently outperform aggressive ones. The most famous demonstration of this came from the political scientist Robert Axelrod, who in the early 1980s ran a series of computer tournaments pitting different strategies against each other in a repeated prisoner's dilemma. The winner, across hundreds of rounds and dozens of competing strategies, was tit for tat, cooperate on the first move, then mirror whatever the other player did on the previous move, reward cooperation with cooperation, punish defection with defection. Keep it simple. Tit for tat won not because it was clever. It won because it was stable. Aggressive strategies burned through their opponents quickly, but then had no one left to exploit. Cooperative strategies that never punished defection were easily taken advantage of. Tit for tat struck the balance. Willing to cooperate, capable of retaliation, and transparent in its logic. Over time, populations of tit for tat players outcompeted populations of pure defectors. Now apply this to the galaxy. If civilizations persist for millions of years, and the Dark Forest assumes they do, since short-lived civilizations would not pose a threat, then they are not playing a one-shot game. They exist in a galaxy with a finite number of neighbors, and the likelihood of repeated encounters, either directly or by reputation, increases over time. A civilization known for destroying others on sight would eventually face coalitions of survivors who cooperate specifically to counter that threat. A civilization known for reliable, reciprocal cooperation would attract allies and trading partners. Over millions of years, the incentive structure shifts from strike first to build relationships. The Dark Forest assumes that the chain of suspicion makes trust impossible. But iterated games show that trust does not require certainty. It requires only a pattern of behavior observed over time. You do not need to read another civilization's mind. You need only to observe that they have consistently cooperated in previous encounters. This is exactly how trust works on Earth, not through telepathy, but through track records. There is a counter-argument here, that the distances between stars make repeated interaction impractical. If a round of communication takes centuries, the iteration rate is so slow that the iterated game effectively collapses back into a series of one-shot encounters. This is a fair point, but it assumes that civilizations interact only through direct messaging. In a galaxy with multiple civilizations, information about behavior can spread through third parties. If Civilization A cooperates with Civilization C and Civilization B learns about it, B has data about A's behavior without ever interacting with A directly. Reputation networks can form even when individual interactions are slow. The third objection concerns the practical physics of interstellar warfare. The Dark Forest assumes that detecting a civilization is functionally equivalent to being able to destroy it. But the engineering required to actually annihilate a world across interstellar distances is far more demanding than the hypothesis suggests. The most commonly discussed weapon in Dark Forest scenarios is the relativistic kill vehicle, an object accelerated to a significant fraction of the speed of light and aimed at a target star system. The kinetic energy of an object traveling at even 10% of light speed is staggering. A projectile the mass of a small car, traveling at that velocity, would strike with the energy of a large nuclear weapon. Scale it up to the mass of an asteroid, and you have a planet killer. But building and launching such a weapon is not simple. Accelerating a massive object to relativistic speeds requires energy inputs that would strain even a Type II civilization. The projectile must be aimed with extraordinary precision at a target that is light years away, accounting for the target system's motion through space over the decades or centuries the projectile is in transit, and the attacker must assume that the target has not moved, developed countermeasures, or incoming threat during that transit time. A civilization advanced enough to be worth worrying about is, by definition, advanced enough to potentially detect and respond to an incoming relativistic projectile. At even a fraction of light's speed, such a weapon would produce detectable signatures. A bow shock of interstellar medium being compressed, a thermal signature from friction with dust and gas, gravitational perturbations as it passes through star systems along the way. The target would not be defenseless. It would have years, possibly decades, of warning, and then there is the problem of retaliation. Launching a relativistic kill vehicle is not a quiet act. The energy expenditure is enormous. The launch signature is detectable. The trajectory can be traced back to the point of origin. An attacker does not simply eliminate a rival and remain hidden. It reveals itself in the act of striking. And if the target has allies, or if the target has already seeded backup colonies in other star systems, the attack may not even accomplish its goal. You have exposed your own position, spent enormous resources, and potentially created a set of survivors who now know exactly where you are and have every reason to retaliate. This does not mean interstellar warfare is impossible. It means it is expensive, uncertain, and self-defeating in ways the dark forest tends to gloss over. The hypothesis presents preemptive strikes as low-cost and decisive. The physics suggests they may be neither. The fourth objection is one of, and in many ways, the most reassuring. It concerns Earth's actual visibility. The dark forest scenario derives much of its emotional power from the image of humanity, broadcasting its position into the void. And it is true that we have been emitting electromagnetic radiation for over a century. But the strength of that radiation drops off with distance, according to the inverse square law. Double the distance, and the signal is 4 times weaker. Triple the distance, 9 times weaker. By the time Earth's television broadcasts have traveled even a few light years, they are fainter than the background noise of the cosmos. A civilization 20 light years away would need an antenna the size of a continent to pick up an episode of a television show from Earth. At 100 light years, the signal is effectively undetectable by any technology we can currently conceive of. The deliberate transmissions, the Arecibo message, the signals sent by METI researchers, are more powerful but extremely narrow and brief. The Arecibo message was a single pulse aimed at a star cluster 25,000 light-years away. It will not arrive for 25,000 years. It was a demonstration, not a sustained broadcast. METI transmissions have been sporadic, low-powered by interstellar standards, and aimed at a tiny handful of targets. The idea that Earth is a blazing beacon in a dark cosmos makes for a vivid metaphor, but the physics tells a different story. We are more like a candle seen from the other side of an ocean, technically emitting light, but practically invisible against the glare of everything else. If the dark forest is the reason for the great silence, it does not explain why we have not been targeted, because we are barely detectable in the first place. The fifth objection is more philosophical, but no less important. The dark forest assumes that every civilization in the universe, regardless of its biology, its history, its psychology, or its stage of development, will converge on the same strategic calculus. Survival above all, suspicion as the default, preemption as the rational response. But why should we assume that intelligence everywhere produces the same logic? On Earth alone, we have examples of wildly different approaches to cooperation and conflict within a single species. Some human societies developed elaborate systems of trade and diplomacy that spanned continents. Others remained isolated by choice. Some responded to strangers with violence. Others responded with gifts. The variation in human behavior is enormous, and we share 99% of our DNA. Alien civilizations, shaped by entirely different evolutionary pressures, different biochemistries, different sensory worlds, and different social structures, might produce forms of intelligence that approach the question of interstellar contact in ways we cannot currently imagine. Imagine a hive mind species with no concept of individual survival might not place the same weight on self-preservation that Lu's axioms demand. A post-biological civilization, one that has uploaded its consciousness into digital substrates, might have no resource needs at all in the traditional sense. A species that evolved in a cooperative symbiotic relationship with other organisms on its home world might default to trust rather than suspicion, because that is what its entire evolutionary history rewarded. The dark forest treats intelligence as a converging phenomenon, one that inevitably arrives at the same conclusions regardless of its origins. But intelligence on Earth has already shown extraordinary diversity in its strategies, values, and responses to uncertainty. Extending a single strategic framework across the entire cosmos is a leap that the hypothesis does not adequately justify. The sixth objection targets a practical gap in the dark forest's internal logic. If the dominant strategy is to destroy any civilization you detect, then someone must be doing the detecting and the destroying. But the hypothesis also states that every surviving civilization hides. This creates a tension. Who is carrying out the strikes? If everyone hides, no one is searching. If no one is searching, there is no threat. If there is no threat, there is no reason to hide. The logic begins to eat itself. Liu addresses this partially through the concept of dark forest strikes. Attacks launched not by a specific rival, but by any civilization that happens to detect a signal. The universe, in this view, functions as a kind of distributed immune system, where any exposed civilization is eliminated by whichever hidden observer happens to notice it first. But this requires that hidden civilizations are actively monitoring the cosmos at all times, which itself requires energy expenditure and technological infrastructure that could, in principle, be detected. Perfect concealment and active surveillance are in tension with each other. The more you invest in watching, the more you risk being seen. There is also the question of cost. Building and launching a relativistic kill vehicle. Every time you detect a faint radio signal from a distant star is not a trivial commitment. If the galaxy contains thousands or millions of civilizations, and each one occasionally emits a detectable signal, the number of strikes required to maintain the dark forest equilibrium becomes enormous. At some point, the cost of constant preemptive warfare exceeds the cost of simply living with the risk of a neighbor. The seventh and perhaps deepest objection is the one that turns the dark forest back on itself. The hypothesis claims to describe a universal logic, a conclusion that any sufficiently rational civilization would reach. But the axioms from which it derives are not universal truths. They are projections. The first axiom, that survival is the primary drive of every civilization, is drawn from evolutionary biology on Earth. Life on this planet has been shaped by billions of years of competition for scarce resources in a closed ecosystem. Our brains are wired to perceive threats, to prioritize self-preservation, to treat strangers with caution. These are deep patterns burned into our neurology by natural selection. When we look at the cosmos and imagine what other civilizations might do, we instinctively project these patterns outward. We assume the universe operates by the same rules that govern the savanna, the battlefield, and the marketplace. But this is a bias, not a law. The dark forest takes the psychology of a species that evolved under specific conditions on a specific planet, and elevates it to a cosmic principle. It assumes that competition and mistrust are features of intelligence itself, rather than features of a particular kind of intelligence shaped by a particular history. This may be true. It may also be a profound failure of imagination, an inability to conceive of minds that do not share our fears. The second axiom, finite resources driving competition, suffers from a similar problem of scale. Scarcity is the defining condition of life on Earth. Every organism competes for food, water, territory, and mates. This is so deeply embedded in our experience that it feels like a law of nature. But at the scale of a galaxy, with hundreds of billions of star systems, each one containing more energy and material than any single civilization could consume. In millions of years, the scarcity that drives conflict on Earth may simply not apply. We are projecting the economics of a crowded planet onto a cosmos that is, by any reasonable measure, absurdly abundant. None of this proves the dark forest is wrong. It is possible that the axioms hold, that the logic is sound, and that the universe really does operate as a silent, paranoid arena. The objections do not demolish the hypothesis, but they demonstrate that it rests on a series of assumptions, each of which can be reasonably challenged. The dark forest is not a theorem. It is a model, elegant, internally consistent, and built on premises that have not yet been tested against a single data point from beyond our own world. Its power lies not in its certainty, but in the fact that we cannot yet rule it out, and in a domain where the consequences of being wrong are as severe as extinction, even a possibility commands respect. But possibility is not the same as probability, and the distance between a compelling argument and a proven truth is, in this case, as vast as the space between stars. On September 5, 1977, a rocket launched from Cape Canaveral carrying a spacecraft called Voyager 1. Its primary mission was to photograph Jupiter and Saturn, to send back images of cloud bands, ring systems, and moons that no human eye had ever seen up close. It accomplished that mission beautifully. But what made Voyager 1 extraordinary was not the photographs. It was what happened after. Once its planetary flybys were complete, Voyager 1 kept going. It had enough velocity to escape the gravitational pull of the Sun entirely, and no one told it to stop. It crossed the orbit of Neptune. It passed the boundary where the solar wind gives way to interstellar space. And it is still going, right now, at this moment, traveling at roughly 17 kilometers per second through the void between stars. Bolted to the side of Voyager 1 is a golden phonograph record. The record contains 115 images encoded in analog form. Photographs of Earth, its continents, its people, its cities. It contains greetings in 55 languages. It contains 90 minutes of music, from Bach to Chuck Berry to a Navajo night chant. It contains the sound of rain, of wind, of a human heartbeat. And engraved on the cover is a diagram. The diagram uses the positions of 14 pulsars, rapidly spinning neutron stars that emit electromagnetic pulses at precise, measurable intervals to triangulate the exact location of our Sun within the Milky Way. It is, in essence, a map. A map showing anyone who finds it exactly where we are. This was considered, at the time, an act of profound optimism. Carl Sagan, who chaired the committee that designed the record, described it as a message in a bottle cast into the cosmic ocean. The assumption was generous and hopeful, that any civilization advanced enough to intercept Voyager would be wise enough to treat the encounter with curiosity rather than hostility. 3 years before Voyager launched, an even more deliberate act of communication had already taken place. In November 1974, the Arecibo radio telescope in Puerto Rico. At the time, the largest single-dish antenna in the world was used to beam a carefully encoded message toward Messier 13, a dense cluster of roughly 300,000 stars located about 25,000 light-years away. The message was brief, 1,679 binary digits, arranged in a grid that, when decoded, revealed a pixelated image of a human figure, the structure of DNA, a map of the solar system, and the numbers 1 through 10. The Arecibo message was largely symbolic. Its target is so far away that no reply could arrive for 50,000 years. But it established a precedent. Humanity had moved from passively leaking electromagnetic noise to actively, intentionally directing a signal at another star system. The transition from accidental visibility to deliberate announcement had begun. And it did not stop there. In the decades that followed, a small but persistent community of scientists and enthusiasts pushed the idea further under the banner of METI, messaging extraterrestrial intelligence. Where SETI listens, METI transmits. The argument is straightforward. If every civilization in the galaxy is listening and none is transmitting, the silence is self-perpetuating. Someone has to go first. METI advocates believe that someone should be us. Between 1999 and 2009, a series of transmissions known as cosmic calls were beamed toward nearby sun-like stars using a Ukrainian radio telescope. In 2008, a message was sent toward the star Gliese 581, a red dwarf roughly 20 light-years away, known to host at least one planet in its habitable zone. The content of that message was crowdsourced. Thousands of text messages collected from the public and bundled into a single transmission. Other projects have sent music, mathematical sequences, and encoded images. Each of these efforts was small in scale. None had the power or duration to stand out dramatically against the background noise of the cosmos. But each one represented a conscious decision by a group of human beings to make Earth more visible than it would otherwise have been. And each one was made without anything resembling global consensus. This is where the practical dimension of the dark forest debate becomes uncomfortable. Set aside the question of whether the hypothesis is true. Focus instead on the decision-making process. Who authorized these transmissions? Who weighed the risks? Who consulted the 7 billion other people on the planet whose fate might, however improbably, be affected by the decision to shout into space? The answer, in most cases, is nobody. The Arecibo message was approved by the observatory staff and a small group of scientists. The cosmic calls were organized by a private researcher with access to a radio telescope. METI International, the primary organization advocating for deliberate transmissions, is a small non-profit. There is no international treaty governing messages sent to extraterrestrial civilizations. There is no United Nations protocol. There is no body with the authority to say yes or no on behalf of the species. This is not a hypothetical governance gap. It is an active one. In 2015, a group of prominent scientists and public figures, including the physicist Stephen Hawking, the entrepreneur Elon Musk, and a number of leading SETI researchers, signed an open statement urging caution. The statement did not claim that the dark forest was correct. It simply argued that a decision with potentially irreversible consequences for all of humanity should not be made by a handful of individuals without broader consultation. The statement called for an international discussion before any further high-powered transmissions were sent. The response from the METI community was mixed. Some agreed in principle, but argued that the risk was overstated. Others pointed out that Earth's electromagnetic leakage had already been spreading for over a century, and that deliberate transmissions added only marginally to our existing visibility. Still others argued that the potential benefits of contact, access to advanced knowledge, confirmation that intelligence is not alone in the universe, outweighed the speculative risks. Hawking himself had been vocal on the subject for years. In a 2010 documentary, he drew an analogy that cut through the theoretical abstractions with blunt clarity. He compared a potential alien encounter to the moment when the indigenous peoples of the Americas first encountered European ships on their coastlines. The Europeans came with superior technology, different values, and an economic model that treated the existing inhabitants as obstacles to be displaced. The encounter was not an exchange between equals. It was a catastrophe for one side and an expansion of power for the other. Hawking was not claiming that alien civilizations would necessarily behave like European colonizers. You're making a structural point. When two civilizations meet, and one is significantly more advanced than the other, the outcome is determined not by the intentions of the stronger party, but by the power differential itself. Good intentions do not prevent displacement. Curiosity does not prevent exploitation. The record of contact between unequal civilizations on Earth is overwhelmingly one of disruption, absorption, or destruction of the weaker by the stronger. Whether or not this pattern would hold at an interstellar scale is unknowable. But the analogy carries weight precisely because it is grounded in evidence. We do not need to speculate about how unequal contact between civilizations plays out. We have thousands of years of documented examples, and the pattern is consistent enough to serve as a warning. The deeper issue is not whether any single transmission will bring disaster. The probability of any specific message reaching a hostile civilization and triggering a response is, by any reasonable estimate, extraordinarily low. The issue is the principle underlying the decision. We are taking an action that is irreversible. A signal, once sent, cannot be recalled. In a domain where we have essentially zero empirical data about the risks. We do not know if anyone is listening. We do not know what they would do if they heard us. We do not know whether the dark forest is real or imaginary. And yet, we are acting as though the answer does not matter. There is a concept in risk analysis called the precautionary principle. It states that when an action carries a risk of severe or irreversible harm, the burden of proof falls on those who wish to take the action, not on those who wish to prevent it. The principle does not require certainty that harm will occur. It requires only that the harm, if it did occur, would be catastrophic enough to justify caution in the absence of certainty. By this standard, the case for caution around deliberate interstellar messaging is strong. The potential downside, however unlikely, is existential. The potential upside, in the near term, is essentially zero. No transmission we have sent so far has had enough time to reach a promising target and generate a reply. The earliest any response to the cosmic call transmissions could arrive is the late 2030s, assuming someone is listening at the target star and replies immediately. For the Arecibo message, the wait is measured in tens of thousands of years. We are, in effect, taking a risk with no immediate payoff and no ability to undo it. And we are doing so without the informed consent of the vast majority of the species on whose behalf the risk is being taken. This is not an argument against SETI. Listening carries no risk. A radio telescope pointed at the sky reveals nothing about Earth's location. The act of searching for signals is purely passive and universally supported by the scientific community. The controversy is entirely about the act of transmitting, about crossing the line from observer to participant. There is also a subtler dimension to this debate that rarely gets discussed. Even if our current transmissions are too weak to be detected at interstellar distances, our technology is advancing rapidly. Radio telescopes are growing more powerful. Directed energy systems, lasers capable of pushing small spacecraft to a fraction of light speed, are already being prototyped. The Breakthrough Starshot initiative, announced in 2016, aims to use a ground-based laser array to accelerate a fleet of tiny probes toward Alpha Centauri. If that technology matures, it could also be used to send a signal of extraordinary power and focus toward any target in the galaxy. We are approaching a threshold. Within a generation or two, humanity may possess the ability to send transmissions that are genuinely detectable across hundreds or thousands of light years. The decisions we make about how to use that capability and the governance frameworks we build or fail to build around it will matter far more than anything we have done so far. The dark forest hypothesis, whatever its ultimate validity, has performed a valuable service by forcing this conversation. Before Liu Cixin's novel brought the idea to global attention, the default assumption in most discussions of extraterrestrial contact was optimism. Aliens would be friendly, or at least indifferent. Contact would be a moment of wonder. The possibility that it could be something else, something dangerous, something irreversible, was treated as fringe speculation, not worthy of serious institutional attention. That is no longer the case. The debate is real now. Governments, scientific organizations, and policy institutes are beginning to grapple with questions that a decade ago would have seemed like science fiction. Should there be an international protocol for deliberate transmissions? Who should have the authority to speak for Earth? What standards of evidence should be met before a signal is sent? What happens if a signal is received? Who decides how to respond and on what timeline? These are not abstract questions. They are governance questions, the same kind that arise whenever a new technology creates risks that cross national borders and affect populations who did not consent. Climate policy, nuclear non-proliferation, genetic engineering. The pattern is familiar. The technology moves faster than the institutions, and by the time the rules catch up, the most consequential decisions have already been made. We are not yet at the point of no return. Our signals are still faint. Our deliberate transmissions have been few and weak. The window in which to establish norms, build institutions, and develop a coherent planetary strategy for interstellar communication is still open. But windows close, technologies mature, and the temptation to act unilaterally, to be the one who makes first contact, who sends the message that changes everything, is not going to diminish. What we do in the next few decades may determine not just whether we are heard, but whether being heard is something we survive. There is a temptation, when confronting an idea like the dark forest, to treat it as a statement about the universe. It describes how alien civilizations behave. It explains why the cosmos is silent. It maps the logic of survival onto a canvas of billions of galaxies and trillions of stars. The scale of the claim is so vast that it feels like cosmology, like a law written into the fabric of reality itself. But there is another way to read it, and this reading may be more important than the hypothesis itself. The dark forest is not just a theory about what is out there. It is a theory about what is in here, inside, the minds that produced it. It is a mirror, and what it reflects is not the cosmos. It is us. Every assumption in the dark forest framework maps directly onto patterns in human history. The first axiom, that survival is the primary drive of every civilization, is a principle extracted from 4 billion years of evolution on a single planet, where every organism that exists is the descendant of ancestors who outcompeted, outran, or outlasted their rivals. The second axiom, that resources are finite and competition is inevitable, is the foundational experience of a species that spent most of its existence in small groups fighting over territory. water, and food. The chain of suspicion, the inability to trust a stranger whose intentions cannot be verified, is a social dynamic that has shaped human politics from tribal warfare to nuclear standoffs. Liu Cixin did not pull these ideas from the vacuum of space. He pulled them from the soil of Earth. And the question that hangs over the entire hypothesis is whether those patterns are universal properties of intelligence or local properties of a particular species on a particular world, at a particular stage of its development. This is not a trivial distinction. It is the distinction that determines everything. If the patterns are universal, if every form of intelligence, regardless of its origin, inevitably arrives at suspicion, competition, and preemptive aggression, then the dark forest is not a hypothesis. It is a diagnosis. The universe is dangerous by nature, and no amount of wisdom, cooperation, or good intention can change the underlying math. The silence is permanent. Contact is lethal, and the only sane response is to hide. But if the patterns are local, if they are products of human evolution, human psychology, and human history rather than fundamental features of mind itself, then the dark forest is something else entirely. It is a confession. It is humanity looking into the cosmos and seeing its own reflection, then mistaking that reflection for a photograph of what is actually there. The history of science is full of moments like this. For centuries, Europeans believed the world was divided into civilized and savage peoples, and they built elaborate theories. Racial hierarchies, stages of social development, natural orders of dominion, to justify that belief. These theories felt rigorous. They had internal logic. They were supported by the best evidence available at the time, and they were wrong. Not because the observations were entirely fabricated, but because the framework used to interpret them was shaped by the observer's own position in the world. They saw what their assumptions allowed them to see. The dark forest may be making the same kind of error at a cosmic scale. It observes that life on Earth is competitive, that trust between strangers is fragile, and that technological power tends to be used aggressively. It then takes these observations and extends them to every possible form of intelligence in the universe, across billions of years and billions of light years. The extrapolation is breathtaking in its ambition, but the data it rests on comes from a single example. One planet, one biosphere, one species, one sliver of time. Consider what we actually know about the relationship between intelligence and cooperation. On Earth, the most successful species, measured by population, geographic range, and ecological dominance, are not the most aggressive. They are the most cooperative. Ants, which operate as collective superorganisms, outnumber every other terrestrial animal by biomass. Humans did not rise to dominance through individual strength or speed. We rose through language, social organization, shared knowledge, and the ability to coordinate action across groups of thousands and eventually millions. The human brain did not evolve primarily to fight. It evolved primarily to navigate social relationships, to track alliances, anticipate others' intentions, communicate complex ideas, and build trust over time. Aggression exists in our species deeply and undeniably, but it coexists with an equally deep capacity for empathy, reciprocity, and collective problem-solving. The story of human civilization is not a story of pure competition. It is a story of competition and cooperation in constant, dynamic tension, with cooperation winning often enough to produce language, agriculture, cities, science, and a global communication network that allows a person on one continent to share an idea with a person on another in less than a second. If cooperation is this central to the only example of intelligence we have, what justification is there for assuming that intelligence elsewhere would default to aggression? The dark forest treats cooperation as a fragile exception and suspicion as the baseline. Earth's own history suggests the opposite may be equally plausible. That cooperation is the engine of complexity, and that intelligence, wherever it arises, may be more likely to build bridges than to burn them. There is a deeper layer to this argument. The dark forest assumes that civilizations remain essentially static in their values as they advance technologically. A species that develops interstellar travel is imagined to be the same species, with the same fears and the same strategic instincts as the one that first split an atom or sharpened a stone. But there is no reason to assume this. On Earth, moral and social development have not kept pace with technological development. That much is obvious. We split the atom decades before we developed the institutional frameworks to manage nuclear weapons safely. We built a global information network before we understood its effects on democracy and mental health. The lag between capability and wisdom is one of the defining features of our current moment. But the lag is not permanent, and the direction of change is not random. Over centuries, the moral circle of human concern has expanded. Slowly, unevenly, with terrible reversals, but expanded nonetheless. Practices once considered normal, slavery, public torture, the subjugation of entire populations on the basis of ethnicity, are now recognized as moral catastrophes by the vast majority of humanity. Rights have been extended to groups that were once considered property. International institutions, however imperfect, exist to mediate disputes that would once have been settled by slaughter. This trajectory is not guaranteed to continue. It could reverse. Civilizations can collapse, and moral progress can be undone in a generation. But the pattern suggests something important, that intelligence, given enough time and enough pressure, tends to develop broader circles of empathy and more sophisticated frameworks for cooperation. Not inevitably, not without setbacks, but as a tendency, a gravitational pull toward recognizing that the well-being of others is connected to your own. A civilization 1,000,000 years older than ours, let alone 1 billion years older, would have had time to undergo transformations in values that we cannot currently anticipate. To assume that such a civilization would still operate on the logic of preemptive strikes and paranoid concealment is to assume that moral development hits a ceiling somewhere, that no amount of time or experience can push a species past the strategic calculus of a Cold War. That is a deeply pessimistic assumption, and it is entirely unsupported by evidence. There is also the question of what advanced intelligence actually wants. The dark forest assumes that civilizations expand endlessly, consuming more resources, occupying more space, projecting more power, because that is what civilizations on Earth have done. But expansion is driven by need, and need changes as capability grows. A post-scarcity civilization, one that has mastered fusion energy, molecular manufacturing, or whatever technologies lie beyond our current horizon, may have no material reason to expand at all. Its members may turn inward toward art, mathematics, philosophy, the exploration of consciousness, the construction of virtual realities richer than any physical environment. The assumption that advanced civilizations are perpetual expansionists is, again, a projection from human history. Specifically from the history of European colonialism, which was itself driven by specific economic and political conditions that may have no analogue in a species that has solved the problem of scarcity. The philosopher Nick Bostrom has written about what he calls a singleton civilizations, entities that have achieved internal coordination so complete that they function as a single decision-making agent. A singleton would not be riven by the internal factions that the chain of suspicion posits as a problem. It could make binding commitments. It could offer verifiable assurances. It could enter into agreements with other singletons and enforce them. The chain of suspicion depends on the assumption that civilizations are internally fragmented and externally opaque. A singleton breaks both of those conditions. Whether singletons are possible, desirable, or common is an open question. But the concept illustrates how narrow the Dark Forest's assumptions really are. It imagines a universe populated by civilizations that are just like us, fractured, fearful, unable to commit credibly, trapped in the same strategic dilemmas that have defined human geopolitics for centuries. The moment you allow for the possibility that civilizations might be fundamentally different in structure, values, or cognition, the entire framework begins to loosen. And then there is, perhaps, the most unsettling possibility of all, that the Dark Forest is not a description of reality, but a self-fulfilling prophecy. If a civilization believes the Dark Forest is true, if it adopts concealment, suspicion, and preemptive aggression as its operating principles, then it will behave in exactly the way the Dark Forest predicts. It will hide. It will treat every detected signal as a threat. It will strike first when it can, and its behavior will, in turn, confirm the hypothesis for anyone observing it. The Dark Forest does not need to be true in order to produce the outcomes it describes. It only needs to be believed. This is a dynamic familiar from international relations on Earth. During the Cold War, both the United States and the Soviet Union operated under the assumption that the other side was preparing for a first strike. This assumption drove both sides to build ever larger arsenals, to adopt launch-on-warning postures, and to interpret ambiguous signals as evidence of hostile intent. The arms race was not caused by actual aggression. It was caused by the assumption of aggression, a shared belief that created the very conditions it feared. The same dynamic could operate at a cosmic scale. A universe in which every civilization adopts the Dark Forest posture would look exactly like a universe in which the Dark Forest is true. Silent, hostile, and lethal, even if the underlying reality were far more nuanced. The hypothesis generates the evidence for its own validity. Breaking out of that loop requires something extraordinarily difficult: the willingness to act on a belief that has not yet been proven, to take a risk that cannot be fully justified by the available data, to extend trust before trust has been earned. On Earth, every major leap in cooperation has required exactly this kind of risk. The first human tribes that chose to trade with strangers rather than kill them were taking a gamble. The architects of the post-World War II international order were building institutions on the hope, not the certainty, that former enemies could become partners. Every peace treaty, every diplomatic opening, every act of unilateral de-escalation has been a bet placed against the logic of suspicion. And while many of those bets have failed, enough of them have succeeded to produce the interconnected, mostly non-warring global civilization that exists today. The question the Dark Forest ultimately asks is whether that pattern can scale, whether the same impulse that led two rival tribes to put down their weapons and share a meal can operate between species separated by light years and millennia. Whether trust, that most fragile and most powerful of human inventions, has any meaning in a cosmos where the distances are vast, the strangers are truly strange, and the stakes are absolute. We do not know the answer. We cannot know it without more data than we currently possess. And the only way to get that data may involve the very risks the Dark Forest warns against. This is the paradox at the center of the question. To learn whether the universe is safe, we may have to do something unsafe. To find out whether trust is rewarded, we may have to trust first. There is a scene in Liu Cicin's novel that crystallizes this tension with painful clarity. A character, contemplating the logic of the dark forest, observes that the tragedy is not that civilizations destroy each other. The tragedy is that they might have been friends, that the very act of preemption forecloses the possibility of the relationship that could have made preemption unnecessary. The hunter in the forest does not know whether the shadow between the trees is an enemy or a potential ally, and because the cost of guessing wrong is extinction, the hunter shoots. Every time. Whether that is wisdom or cowardice depends on something we do not yet have the ability to test. What the shadow actually is. We are a young species. We've been aware of the Fermi paradox for 76 years. We have been capable of sending deliberate interstellar signals for barely 50. Our understanding of the cosmos, while magnificent compared to our ancestors, is still fragmentary, still shaped by the limitations of instruments that can survey only a fraction of the sky at a fraction of the frequencies where communication might occur. We are, in cosmic terms, infants, just beginning to open our eyes, just beginning to formulate the questions that will define our relationship with whatever else is out there. The dark forest is one possible answer to those questions. It may be the correct one, but it is worth pausing before we accept it to notice where it comes from. It comes from a species that evolved through competition on a resource-scarce planet that has spent most of its history in conflict, and that has only recently begun to develop the tools and the instincts for large-scale cooperation. It comes from us. And the universe may be larger, stranger, and more generous than our fears allow us to imagine, or it may not. That is the honest answer. We do not know, and sitting with that uncertainty, neither retreating into paranoia nor leaping into reckless optimism, may be the most important thing our species learns to do. There is, right now, an invisible sphere expanding outward from Earth at the speed of light. It is made of electromagnetic radiation, the accumulated noise of a century of broadcasts, radar pulses, satellite signals, and a handful of deliberate transmissions aimed at distant stars. The sphere is roughly 200 light-years in diameter. In a galaxy that stretches 100,000 light-years from edge to edge, it is vanishingly small. A droplet of ink in an ocean, that sphere is everything we have said. Every signal, every announcement, every whisper into the dark. And beyond its edge, in the vast untouched silence that stretches to the farthest observable galaxies, nothing from Earth has ever arrived. The overwhelming majority of the Milky Way has never heard of us. To the universe, at large, we do not yet exist. This is a strange thing to hold in your mind. We live in a world saturated with communication. Signals bounce off satellites, travel through fiber optic cables, pass through our bodies every second of every day. The planet hums with connectivity, and yet, from only a few hundred light-years away, Earth is invisible. A dim, ordinary star orbited by a pale blue dot that has not yet made a sound loud enough to be noticed. The dark forest hypothesis takes this situation and asks what it means. Not in the abstract, philosophical sense, though it does that too, but in the immediate, practical sense. What does it mean to be a species that has just begun to make noise in a universe whose rules it does not understand? What does it mean to be visible in a space where visibility may carry a cost? What does it mean to be new? The honest answer is that we do not know what it means. We do not have enough information to know. The Fermi paradox remains open after 76 years because every proposed solution, including the dark forest, rests on assumptions that cannot yet be tested. We have not detected a single extraterrestrial civilization, which means we have no data points against which to measure any theory. We are reasoning from first principles in a domain where first principles may not be sufficient because the phenomenon we are trying to explain, the behavior of intelligences we have never encountered, may operate according to logics we have not yet conceived. This is an uncomfortable position for a species that has grown accustomed to answering its own questions. We mapped the genome. We photographed a black hole. We built machines that can predict protein structures and translate languages in real time. The arc of modern science has been one of relentless expansion. More data, better models, deeper understanding. The Fermi paradox sits outside that arc. It is a question for which more data may never arrive, or may arrive in a form we are not prepared for. The dark forest is one way of filling that void. It offers a complete, internally consistent story that explains the silence without requiring exotic physics or unlikely biology. Its axioms are drawn from principles that feel familiar: survival, scarcity, suspicion. Its logic proceeds with the precision of a mathematical proof, and its conclusion, while disturbing, has the cold comfort of coherence. If the universe is a dark forest, then at least we understand why it is quiet. At least the silence makes sense, but coherence is not truth. A story can be perfectly logical and still be wrong if its starting assumptions do not match reality. The history of human thought is littered with elegant, internally consistent frameworks that turned out to be built on flawed foundations. Ptolemaic astronomy predicted the movements of the planets with remarkable accuracy for over 1,000 years, and it was wrong. Classical economics modeled human behavior with mathematical precision and missed the irrational, emotional, and social dimensions that drive most actual decisions. The dark forest may belong to this category, a framework so well constructed that it becomes difficult to see past, even when the evidence for it is, strictly speaking, zero, because that is the uncomfortable truth at the center of this entire discussion. There is no evidence for the dark forest. There is no evidence against it. There is only the silence, and the silence is compatible with dozens of explanations, many of which have nothing to do with hiding or hunting. The universe may be quiet because life is extraordinarily rare, and we are among the first to emerge. It may be quiet because civilizations tend to turn inward rather than outward, exploring the depths of consciousness, mathematics, or virtual worlds rather than the physical galaxy. It may be quiet because the distances are too great, the timescales too long, and the methods of communications too different for us to detect anything with our current instruments. It may be quiet because we have been listening for only 60 years, a blink, a fraction of the time it would take for a meaningful exchange to develop across interstellar distances. Or it may be quiet because the forest is real, and every civilization that has made a sound is gone. We cannot distinguish between the above possibilities. Not yet, perhaps not for a very long time, and that uncertainty is itself the most important thing to sit with, not the answer, but the absence of an answer. And what that absence demands of us, it demands humility. We are a species that has been technologically capable for barely 2 centuries, aware of the paradox for less than 1 century, and capable of acting on it. In either direction, contact or concealment, for only a few decades. We are newcomers to a question that may be billions of years old. The idea that we have already figured out the answer on the basis of no empirical data and a handful of axioms borrowed from our own evolutionary history would be extraordinary arrogance. It demands caution. Whatever the truth is, the stakes are unlike anything else our species has faced. If the dark forest is wrong and we hide, we lose nothing but opportunity, and opportunity can be recovered. If the dark forest is right and we broadcast carelessly, the loss is not recoverable. The asymmetry of consequences argues for prudence, even in the absence of proof, and it demands something harder than either humility or caution. It demands that we keep the question open, that we resist the temptation to collapse the uncertainty into a single narrative. whether that narrative is optimistic or paranoid. The dark forest is compelling because it closes the question. It provides a clean, satisfying answer to an unsettling mystery. But closing the question prematurely is itself a risk. It narrows our thinking. It shapes our decisions. It forecloses possibilities we have not yet imagined. The silence of the universe is not a message. It is a blank page, and what we write on it will say more about us than about whatever is actually out there. If we project our fears, we will see a forest full of hunters. If we project our hopes, we will see a cosmos waiting for a handshake. The truth is almost certainly stranger and more layered than either image, because the universe has never been under any obligation to match human expectations. Voyager 1 is still out there. It crossed into interstellar space in 2012, and it is still transmitting a whisper of data from an instrument package running on the radioactive decay of a few kilograms of plutonium. Its signal grows fainter every year. In a few more years, the power will be too low to send anything at all, and the spacecraft will go silent. But it will keep moving. It will drift through the galaxy for millions of years, carrying its golden record, its diagrams, its music, its map. A message from a species that was not sure whether sending it was brave or foolish, but sent it anyway. That is, in the end, where we are, standing at the edge of an answer we cannot yet reach, holding a question we cannot yet resolve in a universe that has given us nothing but silence and the freedom to interpret it. The dark forest may be real. The cosmos may be kind. The truth may be something we lack the language to describe. The only thing we know for certain is that we are here. We are listening, and the night is very large.